Okay, hello everyone, welcome. Um, it's kind of amazing. It is already Friday, um, and I already have a question tossed into the chat window. Let's see what it says. Let's say we have a data entry row x1, x2c, and x1 was real valued, x2 is discrete, bins with at least three discrete values. Would it be effective to split it up into x1, x2a, x2b, x2c when entering into a neural net? Well, we're not talking about neural nets. So if you don't mind, Nathan, I would like to defer that until we are talking about neural nets.
Were we not talking about this a couple lectures ago? I just thought of it.
That was a naive neural net that's not practical.
Okay, but would that method have worked?
Probably not.
Probably not, where you split up the values to be 0 or 1, 0 or 1, or 0 or 1.
No, because for that
First,
particular network, you're assuming all real valued inputs.
but you want to insert some bins into it to train it. So I was thinking that one value would be 0 and one value would be 1, or 0,
Yeah, but
or 0, 0, 1.
it would not work very well because what are the weights then going to be on those connections? They would just be either 0 or 1 weights.
Okay, I got it. Thank you.
Yeah, I mean, we will definitely talk about those issues, honestly, kind of starting next week. Because when we start talking about linear models, some of the first linear models we will look at are linear neural nets.
Okay, thank you.
Yep. Okay, so, oh, and by the way, in case you're worried about it, there are no questions on the quiz about that neural net. All right, so where we're going today, um, we still have a couple algorithms that we need to look at related to your project, but they fall more in the area of unsupervised learning. And you'll recall that the primary distinction between unsupervised and supervised learning was whether or not the data was labeled. Well, for what you'll be doing in the project, even though the data is labeled, there's an unsupervised component where you're basically ignoring those labels. And in particular, we're going to be looking at how we cluster the data. I don't know how many of you took Dr. Neely's data mining class last semester, but I'm sure she spent quite a bit of time talking about clustering, especially since clustering is directly related to her research. We will not be going into any nearly that level of depth in this course. As you'll see, this course is much more focused on the supervised side of things. And so we'll only talk about a couple unsupervised methods. Within the discussion today, my goal is to get through three algorithms. The k-means algorithm, the class of algorithms that we call k-medoids. However, the specific algorithm that we will look at is called partitioning around medoids. Or PAM. And then the third one is an algorithm that I'm not asking you to implement called dbScan, which is a density-based clustering method. Okay, let's see, what else did I want to say before I jumped into the algorithms? Oh, one administrative comment, since I noticed that Giorgio just joined. The first programming assignment has been graded. The grades have been posted. If you have any questions about the grading of your project, please talk to Giorgio first. Since he's the one that graded the assignment, he's the one that will be able to answer your questions the best. If after you've talked to Giorgio, you still have concerns or questions and you're not satisfied, then go ahead and come talk to me and see if we can get that resolved. Any word on what the distribution looks like? To be honest, I only looked loosely. I can say it looked like a normal distribution. So it was sort of what I expected it to be, but I don't remember the values. Okay, so let's start by talking about the k-means algorithm. To do that, we're going to look at an example. So let's suppose we have this data set. And as shown here, it's a real value data set. The data is in 2 dimensions, and you want to be able to cluster this data. Now, one of the advantages that we have with an example like this is we can plot it, and we can, see fairly readily that we have, 5 clusters here. But in a classic unsupervised learning problem, you don't know that. And you're going to be in a high enough dimensional space that it may be very difficult to be able to generate plots like this, even if you do some kind of dimensionality reduction that gives you a good sense of the number of clusters. So, in fact, we are going to proceed as if we don't know. However, the 2 algorithms that we're going to be looking at are going to ask you to guess. And frankly, that guess is going to end up being a tunable parameter. So it's something we talked quite a bit about tuning on the first project. You're going to have to tune here as well. All right, so we have this data set and we want to figure out how to cluster it. Well, there are a couple things that we could do. One, a pretty naive approach is to just say, let's overlay a grid on the data and break it up into 4 groups. Well, the first thing that this has done is it said, we only have 4 clusters. Now, just looking at the data, we know that's wrong. But regardless, that was our assumption. That's the value we're trying to tune. And we've now defined these 4 clusters. Well, looking at that, I think it's pretty safe to say that that's not a very good representation of those clusters. So this is where using something like what essentially amounted to a naive binning, like you were doing when you were discretizing the data, was not a very good approach. All right, so what can we do that's better? Well, one idea that has been proposed is to say, let's start with these 4 bins, if you will, and we're going to represent the cluster using some point within the bin. Now, that point may or may not be an actual example from your data set. And we're going to assume for the sake of discussion that in this case, it's not. Well, for this grid-based approach, the kind of the naive point that we would use to represent our clusters would be the points right smack in the middle. But again, that's not a very good representation of the data here. So another proposal is to say, okay, we've divided the data up into these 4 bins. Let's take the mean point, basically the average over all of the dimensions, and let that be our representative point, which, as you can see, has now shifted. If you look at those, the binary codings, the 00011011, it's now shifted those representative points to what we call the centroid of that particular partition. And if you look at the upper left quadrant, the 00 is not too bad. When you move to the right, 01's not bad, but it's starting to get a little bit off, mostly because of these points, here, that have crossed over to this right-hand partition that really belong to that cluster there. And when we come down to this lower right quadrant, again, the 11's not bad for that cluster, but we still have this problem with these data points down here. In fact, looking at this example, and I didn't generate this example, this comes from Andy Moore. I'm not even sure he's right. I think that the centroid would have been closer down into this region. And then we come over into this one, and the 10, the 1, 0, is actually more reflective of what that centroid would look like. And it's just completely missing the two clusters. So not the greatest idea. Well, what could we do to improve it? This is actually kind of the motivation behind the k-means algorithm, where instead we use those as starting points, and then we would go through and we would reconstruct our clusters based on those centroids, where now we're going to go through and we're going to assign the points closest to those those centroids, regardless of where the initial divisions in those partitions resided. So to give you a little bit of a sense of the motivation, let's actually say we were better, and instead of only having 4 clusters, we really did know that there were 5 clusters. So this shows the idea. And the way you can read this diagram is that the initial points you can think of as our initial guess to the clusters are these little, if you can see the color, red points here, 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 and here. And just looking at the data, again, those aren't very good. But they are now going to allow us to essentially apply a nearest neighbor rule to say, okay, which centroid is closest to each of those individual data points, assign the data point to that centroid, and then recalculate the centroid based on the data points that have been assigned. And when you do that, you see this shifting occur, where now the centroid is moving over, centroid's moving up, we have a little bit of a movement here, this moves over, and so on. Now notice the other thing, overlaid on this diagram are these black lines that are borders essentially separating our current clusters. Now, if you look carefully, that's actually a Voronoi diagram. But it's a Voronoi diagram that has been constructed based only on the centroids. And in particular, this Voronoi diagram corresponds to the green positions after we've moved. And so what we're doing through this clustering process is we're gradually morphing the centroids and morphing the Voronoi regions to better conform to those clusters. This is not the end clustering. We would go back and we would repeat that process until some convergence criterion is met. All right. So I'm going to show you pseudocode, but before we do that, let me take a look to see if there were any questions in the chat window. No. So let me pause, and I'll show you the pseudocode in a second, but let me see if there are any questions first. Okay. So here is pseudocode for doing k-means clustering. And the first thing you'll notice is that we're feeding into the algorithm our data set and that value k. K is the guess at the number of clusters. All right, I need to make a point. When we compare k nearest neighbor to k means, this and this are not the same thing. So this is another unfortunate overloading that has happened in the field as these algorithms were developed, where in the k nearest neighbor algorithm, k is the number of neighbors that you are collecting to do classification, where in k-means, k is the number of clusters. Two entirely different things. All right, so now going back to the pseudocode, we're giving the algorithm this guess, this number k, which is what we are saying we believe the number of clusters to be in the data. And then the first thing we do in line 2 is we initialize a set of, it's shown as means at random. These are actually the starting centroids for our clusters, and we just pick them at random. We're not picking them out of the data set, we're picking them out of the data space within which we're working. And generally, when we're doing that random sampling, it is a uniform sampling. So the idea is that presumably, if you do this enough times, that you're going to cover the space pretty well. And by the way, the k-means algorithm is a greedy algorithm. It's basically a simple hill climb, meaning that it will converge to a local optimum that still might not be the correct clustering. So you may want to run this multiple times to get the best clustering. All right, so here we're just doing it once. We enter this outer repeat loop, which is basically saying keep going until the clusters don't change. Now, you may find as the algorithm is running that there might be a few data points such that you keep bouncing back and forth between them. And so there are these minor wiggles in the cluster centroids. So you may still want to put a maximum number of iterations on this just to get it to stop. All right, but anyway, you go until you're done. And then the inner loop is going to process each of the examples in the data set. So what do? You go and you take a data point and you find which of those means, which of those centroids is closest to that data point. And you assign that data point to that nearest centroid, which is basically saying, I'm saying that based on these centroids, this data point belongs to that cluster. After you have assigned the clusters to all of the different data points, you then go and you update the centroids. You're going to calculate new means just based on that data. Go back and do it again. Go through all of the data, reassign them to their clusters. After you've done that, update the centroids. Go back and do it again. And you just repeat that process as shown here until you get no appreciable change in the centroids. And when you're done, you just return the centroids. And those centroids are the representative points for the K clusters. All right. Are there any questions about that pseudocode? And I can go back and show it to you again if I need to, but.
I may have missed this, but did you say it fixed the local optima issue?
What do you mean, does it fix the local optima issue?
You said that it would get stuck in local optimas.
It will get stuck in local optima, which means that oftentimes you need to run it multiple times.
Would a simulated annealing be effective, hypothetically?
No, because of the data point assignment that you're doing here, it's hard to say what it means to assign or not assign a point to a centroid.
Okay, thank you. I was just curious.
Yeah. I mean, it's an interesting idea, and there may have been some folks that have attempted to apply simulated annealing, but I don't think it buys you much. Any other questions? Okay, I want to make a few points about this algorithm before we move on and look at k-medoids. We already mentioned that k-means essentially is a hill climber. When you look a little bit more closely at the theory behind what k-means is doing, and I don't remember if we talk about this more generically in this class or not, But this corresponds to a method that's also called expectation maximization, or EM. And the expectation maximization algorithm or process is one that attempts to do parameter estimation Well, first, what do we mean by parameter estimation? Effectively, you can think of the clustering as a model, right? And what the model is doing is it is giving you a way to characterize those clusters, and we're doing it via these cluster centroids. So the parameters that we're estimating are the centroids of the clusters. Similar to estimating the weights in Winnow, or estimating the probabilities in naive Bayes. That's also doing parameter estimation. But one of the other important things about expectation maximization is that it involves a mix of observed and unobserved variables. Technically, they're random variables, but again, we're not going to get into that level of detail. So from our perspective here, what are the observed? This is the data, the actual feature values that have been observed for each of the data points. What are the unobserved? These are the cluster centroids. And that's because we can't look directly at the data and have the data tell us what those centroids are. We're trying to discover them. We're trying to uncover them. When we have this mix of observed and unobserved variables, one of the things is these unobserved variables are also sometimes called latent variables. And so the clustering problem is essentially a latent variable modeling problem where you're trying to estimate the parameters for those latent or those unobserved variables. And that's why expectation maximization, or EM, can be applied here. And the EM process, as the name suggests, the first thing we do is we calculate expected values for these unobserved parameters. And then there's a maximization step over the candidates for these expected values that allows us to shift that estimate. That's what's going on with the estimation of the centroids and the reassignment of the points. It's that alternating back and forth between expectation and maximization. Now, I could go through a much more mathematical and theoretical derivation. I'm not going to do that. Any other points I wanted to make? Oh, so if this were a classic clustering problem that you were being asked to do for your project, you might want to try things like K values that are relatively small. 2 clusters, 3 clusters, 5 clusters, 10 clusters. But if you look carefully at what the assignment is asking you to do, you'll notice that these data points are going to end up being proxies for the data set for K nearest neighbor, similar to what you're getting out of either the edited or the condensed algorithms. So you're probably going to need more clusters. So how many clusters? Again, that needs to be tuned, but a common starting point for that kind of an application is somewhere around the square root of n, where n is the number of examples in your data set. So as you start tuning that K, that's where I recommend you start. All right. At this point, I think I'm done with K-means. Let me see if there are any questions. Okay.
New page.
So the next algorithm we're going to look at, as I mentioned, falls in this class of algorithms called K-medoids algorithms. And the specific algorithm we're going to look at is called partitioning around medoids. Okay, so the first thing to notice, let's go back and talk about k-means for just a second. K-means is an example of a partition-based clustering method, where what it's doing is it's going through and it is identifying hard divisions or hard partitions between the clusters within your data set. Well, K-medoids is also a partition-based clustering algorithm. Another thing to notice with K-means, and this is getting to the inductive bias, is that it assumes spherical clusters. Now, if you do some kind of weighting on the features, then you can morph them to be more like a hyperellipsoid instead of hyperspherical. But basically, they're spherical, which also means convex. Well, that's true of K-medoids as well, sort of. And the distinction that we're going to see comes with our definition of what a medoid is. Basically, a medoid is a representative object or member of the data set. So right off the bat, the primary difference between these two methods is that instead of calculating centroids for our clusters, we are going to be clustering by focusing on actual data points in the data set itself and do our partitioning based on those. And those data points are medoids, which is kind of interesting because one of the things that you run into is, think about the distinction between finding the mean of a data set versus finding the median of the data set. What advantage do you get by focusing on a median as opposed to the mean? You can either type it in the chat window, or if somebody wants to unmute and say they can. Less affected by heavy skew. Okay, that's true. There's another way that we normally refer to that, is that this is less affected by outliers. And that's one of the advantages that we will end up getting with K-medoids, where as we're doing the clustering, identifying those clusters become less sensitive to these outlier data points. Okay, now, to do this, what I want to do is I want to talk about objective functions. What are objective functions? They are functions that we are trying to optimize. And when we talk about clustering, there are a number of different objective functions that we could apply. But in general, what we want is we want an objective function that will enable us to allow or to find well-separated clusters where the clusters are compact. In other words, think about calculating the average distance between all of the points that are within the cluster. We want that average distance to be relatively small. And now calculate the average distance between the points in different clusters, and we want that average distance to be large. So we want the clusters separated from each other, but within the cluster, the points to be close together. Okay, so with k-means, we can define something that we're going to call distortion. And we're going to define this as the sum over our clusters, 1 to k, and then we're going to sum over all of the i's, all of the individuals that are located with, oops, hold on, that should be a j, sorry. Within the jth cluster. So we're only considering those points within the jth cluster, and we simply take the difference of the points of the centroids squared. Now, the one thing about this particular measure is it handles the closeness of the points within the clusters very well. It does not really directly address the distance between the clusters. And there are versions of this objective function that could take that into account as well. But we're going to keep it simple and only look at the within cluster distances. So that's k-means. For k-medoids, yeah, I thought so. I'm getting too close to the bottom. Here, do it up here. So the distortion for k-medoids going to sum again over the clusters. Really? And sum over the points in the respective clusters, just like we did before. But now, we're taking the distance to this data point m sub j, which is our medoid. So the nature of the objective function looks very much like k-means. The only difference is whether we're using a centroid or we're using a data point. Okay. Here's the problem. K-medoids is NP hard. finding those best data points is very expensive. And so we're still going to end up having to employ an approximation algorithm to find them. So here's the pseudocode for the PAM algorithm. It's a little bit more complicated, but very similar in structure. We still feed it our data set. We still feed it K, so K still needs to be tuned. And then rather than initializing centroids randomly, we're going to pick from our data set K points M1 through MK, pick those randomly. And you'll notice that the outer loop has the same process where we just keep going until there's no change in the metoids. Now, the nice thing is since we are dealing with actual data points, this will stop. And then you return the metoids when you're done. All right, so now we go into the inner loops. The first thing is that first loop, which looks an awful lot like what we did in k-means, where we're going through and we're assigning all of the data points in our data set to the clusters that have metoids closest to that point. So it's exactly the same thing we saw in k-means. After we have done that, we need to go back and evaluate the quality of the clustering. And so we calculate the distortion measure that we defined for k-metoids in line 8. And now you're going to hold on to that, and we're moving into what is, again, a hill climbing procedure. Now we go and we loop through all of the metoids, in other words, all of the clusters. And within that, we loop through all of the data points, looking at data points that do not belong to our target cluster. And we swap. In other words, we say, let this data point become the new metoid. And now we're going to recalculate the distortion based on that new metoid. If the distortion is not better, then we swap it back. And we do that now pairwise for all of the metoids and data points until there is no improvement in the distortion. And that's where we've hit the local optimum. And then we return those metoids. So the first thing to notice is that this process is more expensive than the k-means process because of this swapping mechanism going on. The good news is, however, that generally the number of passes through that outer repeat loop will be less than what you have in k-means. So yeah, each pass is more expensive, but the overall cost of this algorithm should be comparable. And same recommendation, I would start with k equal to square root of n as your starting point. Okay. Are there any questions about the k-metoids algorithm? Okay. We have 10 minutes left. We should be just right, I believe, for talking about density-based clustering.
New page.
Okay. This is actually a neat algorithm. The full name is density-based spatial clustering of applications with noise. In other words, DB scan. So just to describe the process, suppose this is our data set and we want to cluster it. Now, notice this one's going to be a little bit trickier than what we talked about for both k-means and k-medoids, in that first there's all this noise that can kind of cause the clusters to start to merge together if you're not careful. And the other thing is these clusters are not convex. And you can see that, for example, by looking at this, which you might regard as a cluster, and this, which you might regard as another cluster. And so we want to be able to differentiate those clusters. And looking at this data set, it looks like there should be 1, 2, 3, 4, 5, 6 clusters. All right, so how do we do that? So to do this, we need to define a couple parameters. Okay, so some hyperparameters to tune. By the way, if you hadn't noticed, virtually every machine learning algorithm you're going to come across will have hyperparameters that need to be tuned. Sorry about that. Okay, so the first hyperparameter, we're just going to denote eps, think epsilon. And what this will correspond to is a radius of a hypersphere and you can think of now laying this hypersphere down on top of every single individual data point in our data set. And then another parameter which will denote min points. This is the minimum number of points needed to say a data point is not noise. All right, and so once you've overlaid this hypersphere on top of the data point, you're going to look at how many other points happen to fall inside of that hypersphere. Count them up, and if the count is greater than min points, greater than or equal to min points, you're good. That's not a noisy point. All right, and then this leads us to define 3 different kinds of points. First is what we call a core point, which is a point at center of hypersphere with greater than or equal to min points, other points. Okay. We will also define what's called a border point, which is a point falling within another core point's hypersphere. That is not a core point itself. And then finally, we have noise points, which is anything left. So these are points that are not core points, and they're points that do not fall within the hypersphere of a core point. So graphically, It looks something like this, where in 2 dimensions, if we look down here, this is a core point, because when we look at the circle or the hypersphere around that, and this is assuming min points equals 4, we have more than 4 points there. But over here, this one is a border point because it falls within that circle, but when we put the circle around it, notice it only has 3 other points, which does not exceed the min points. And then finally up here is a noise point because, again, within its circle, we don't have more than 4 points, and it does not fall inside a core points circle. So that shows the classification of these points. And then the algorithm that we use to do, actually, okay, so this is good. This takes our original data that we just showed a minute ago, and what it has done is it has effectively labeled the points where, the big mass of green points, again, those of you who can see the green, if not, all of these points here, all of these points here, those are core points. The blue points, like these here, or some down here, a couple up here, are border points. So they're points that are really close to the core, but they don't have the density necessary to say that they too are core points. And then all of these red points out here are noise. Okay. This is the pseudocode for doing dbScan. Notice we don't have to tell it how many clusters. All we do is we give it the data set, but we do have to have preset epsilon and min points. We set a cluster label. It's our initial cluster. We just set it to some label, for example, 1. And then we go through and consider only the core points. And as we encounter a core point, the first thing we ask, is it labeled? If it's already labeled, we can skip it. If it isn't, then we go ahead and we assign it a new label. Right. And then after we've done that for that point, we look at the neighborhood around that point, again, looking at all of the points. So these are those that are within that hypersphere. And we look to see if any of those points are unlabeled. If they are unlabeled, then we go ahead and assign them to the point that we just labeled and give them the same cluster label. And we do that when we're done. We just return the set of cluster labels as well as the clusterings on the points. What we find is that dbScan will now give us this as our clustering, where lo and behold, we have 6 labels. All right. Are there any questions about dbScan? Can this particular algorithm partition the green core clusters into different labels for each of those individual subclusters? Are you asking if it's possible to get different actual clusterings?
I'm saying like one of those horseshoes would be categorized as one and another horseshoe would be categorized as another one with that particular algorithm we were just going over.
If you actually have horseshoes like this, they will get different labels.
Okay, got it.
But and this is why I thought you asked something different. The thing that gets a little bit tricky here is, depending on how you search those data points, it is possible that one of those horseshoes could be split into 2 clusters, because you're effectively growing the clusters.
Okay, I see.
Yeah.
That makes sense. Thank you.
Yep. Any other questions? I have one really important point I have to make before I let you go, but we have time if you have questions. All right, I'm going to make the point. And unfortunately, if you read the literature, the machine learning literature, the point I'm about to make is often violated. And when they do this, you should immediately get suspicious. Clusters are not the same as classes. Oftentimes you will find researchers that say, okay, I'm going to cluster my data. The data happens to be labeled, and I'm going to evaluate how well my clustering did by using classification-based metrics like 0-1 loss or precision or recall using the labels in the data. That is completely and entirely invalid. There is nothing that guarantees that clusters will correspond to classes. And an example that I have used in the past is, suppose I have a simple 2-class problem, and that line accurately separates the 2 classes. But the data that I have looks like that. In which case, if I did clustering, I have a cluster here, and I have a cluster here. If you use the classification measures to evaluate those clusters, you will get the wrong answer. So I'm flat out telling you, do not equate clusters and classes. Are there cases where they will be the same? Sure, but you can't guarantee it. Are there any questions about that? All right, that's all I have. Have a good weekend, and we'll see you all on Monday. Oh, there's a question here. Sorry. Can this particular algorithm partition the green? Oh, no, that was the old question. Sorry. Okay. Yeah, have a good weekend. We'll see you on Monday.